Welcome to the solutions to the electrostatics problem set, problems number 7 through 9. We start with number 7. An object with a net charge of 24 microcoulombs is placed in a uniform electric field of 610 newtons per coulomb. Directed vertically, what is the mass of the object if it floats in the electric field? Well, if we start with a free body diagram, we know two things here. One, in order for the mass to float, we know that that weight has to be down. So for it to float, that means the electrostatic force on it has to be up. Supposing that the charge is positive, that means the direction of the electric field is also up. Not that that matters in this question, but we're just adding it for the diagram to understand what's going on here. If the electrostatic force is canceling out the weight, we can set them equal to each other. So all we need to know is the electrostatic force, and we can solve for the mass of the object. Well, that comes from E equals F over Q. Isolating that for F, which would be E times Q, 610 newtons per coulomb times 24 times 10 to the negative 6 coulombs equals 1.46 times 10 to the negative 2 newtons. It does not matter that the positive sign was assigned to the charge here. If you don't understand why that is, ask in class. Since the object floats in the field, F equals mg, so we set the force that we just calculated equal to mg, divide by 9.8, and we get a mass of 1.49 times 10 to the negative 3 kilograms. You'll note that this concept is similar to the Millikan oil drop experiment. Not the same because it's some random object instead of an oil drop, but it's the same concept. Moving on to number 8. Determine the electric field strength of a point 1 centimeter to the left of the middle charge shown in the diagram below. And then we have in B, they want the magnitude and direction of the force if we place a negative 2 microcoulomb charge at that spot. Starting with A here, I drew a point right here that is 1 centimeter to the left of the middle charge. And then I'm going to draw the direction of the 3 electric fields on that point due to the 3 charges in the diagram. To keep everything straight, I labeled the charge on the left 1, the charge in the center 2, and the charge on the right charge 3. The electric field due to charge 1 is the direction a positive would take due to that charge. Since charge 1 is positive, the electric field E1 would be to the right. The electric field due to charge 2, since charge 2 is positive, would be to the left, since the direction a positive would take. And the electric field due to charge 3, since charge 3 is negative, it would attract a positive, so the electric field due to charge 3 is also to the right. It then makes sense that the net electric field would be E1 plus E3, since they're both pointed in the same direction, minus the electric field due to charge 2. Calculating and substituting and calculating, you would substitute 9 times 10 to the 9th for K. I'm just substituting K, but you would use the actual value there. Times the individual charge for 1, 6 times 10 to the negative 6 for micro. For charge 3, 2 times 10 to the negative 6. And for charge 2, 1.5 times 10 to the negative 6. Let's go back here. Why is a negative not assigned to this charge? Because we already took into account, based on determining the direction of the electric field, the fact that it was negative. What is obvious to you in these calculations here is we don't include sign of our charges in doing the calculations, because we already took into account the fact that it was negative when we designated the direction for its electric field. The distances for each E1 is 2 centimeters from that point. That point is 2 centimeters from charge 1. That point is 1 centimeter from charge 2, which we see over here. And that point is 3 centimeters from charge 3, which is 2 centimeters plus the 1 centimeter to the left of that. Don't forget to square. In doing that calculation, we get 2 times 10 to the 7th newtons per coulomb. And because we got a positive value, that indicates to us that the net electric field is to the right. Now for B, E equals FE divided by Q. We know our net electric field at that spot is 2 times 10 to the 7th. FE divided by the charge we're going to put at that spot, negative 2 times 10 to the negative 6. And we get an answer that's 40 newtons. We get an answer that's negative 40 newtons. And the negative indicates to us that the force is in the opposite direction of the electric field, which makes sense since electric field direction is defined to be the direction a positive would take. This charge is negative, so it would be pointed, the force on that charge would be pointed in the opposite direction. Lastly, number 9, an electron is accelerated by a constant electric field of magnitude 300 newtons per coulomb. Find the acceleration of the electron and find the electron's speed after 1 times 10 to the negative 8 seconds, assuming it starts from rest. This is a nice problem that incorporates concepts that you've learned previously with Newton's second law and kinematics in our electrostatics unit. Nice AP question. We start by using the strength of the electric field and the fact that we know the charge of an electron to solve for the force acting on that electron, which would be 300 times 1.6 times 10 to the negative 19, which would be 4.8 times 10 to the negative 17 newtons. Yes, that force would be negative, but all that tells us is that it's in the opposite direction of the electric field. Taking the magnitude of the force and dividing by the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms, we get an acceleration of 5.27 times 10 to the 13th meters per second squared. We now take that acceleration. We're looking for the final speed of the electron, assuming it starts from rest, so we know its initial velocity is 0 in time. The best kinematics choice would be V equals VO plus AT. The initial velocity is 0. The acceleration we calculated times the time. And that gives us an answer, 5.27 times 10 to the 5th meters per second. More practice with electric field problems as we tackle number 10 and 11 in class tomorrow.